Hey there, this is lucius.lafromboise from QESuite, and we've been talking a lot about normality testing recently. And today we're going to learn a bit more about the different tests and how they compare. That's why we've been learning about a lot of different tests, because they each offer something a little bit different. And if you're going to be using them, it's important to know what those differences are. So again, I just want to go over why we test for normality. So normality is an assumption for many engineering statistics and analyses, mainly process capability. That is one of the go-tos when it comes to any validation activity, or when you really want to look into your process and see how it's doing, we use capability, but it relies on normality. So we use normality tests to determine whether or not our process capability is valid. And then the central limit theorem. We like that because after n equals 30 samples, the variance sort of levels out, so we shouldn't expect much of a change in our process capability. And as engineers, we're always trying to get the best results with the resources we have, including money, and more samples means more money, which will become a very important topic here in a couple of slides when we get to sample sizes. So in QESuite, you have the choice between 6 different normality tests, and you really have a few more because some of them have some variations. So you've got the Anderson-Darling test, you've got the Jark-Barra test, you've got the Kolmogorov-Smirnov test, and the Lilliefors corrected KS. So if you remember, the Lilliefors uses the KS test statistic, but then calculates a different p-value. And in this video, we are going to actually learn why it's called the Lilliefors corrected KS. It's a super interesting story, and I can't wait to get into that. We also have the Ryan-Joyner test. In the Ryan-Joyner, similar to Lilliefors, but instead of being based on the KS test, it's based on that final Shapiro-Wilk. So the Ryan-Joyner is an approximation of the Shapiro-Wilk that is trying to approximate, get a similar power, but make it more computationally efficient. Then in the Shapiro-Wilk, you have a couple of different methods of calculating. You have the Shapiro-Wilk using tables, you have the Shapiro-Wilk using an approximation equation, and then you have the Shapiro-Wilk-Royston. So we are going to get into a lot of this stuff here and figure out why so many tests. Well, as engineers, we know that every method has drawbacks and advantages. And we also know that it's good to use multiple checks to ensure the integrity of our data. Okay, so like sometimes a test is going to be too strict for small deviations from normality. So generally that's kind of what we're looking for, is a stricter test. But sometimes it's too strict and our data is good, our capability is excellent, and we really just we want to be able to use the data because it looks good. Great capability, but we're failing normality on a really strict test. Maybe we'll want to open that up a little bit. Who knows? Maybe we will see a normal distribution. Okay, so how do we evaluate the effectiveness of a normality test? Well, in general, we use what's called the power. And so the power is a measure of the test's ability to correctly reject the null hypothesis. So that means if you've ever heard of type 2 error, which is type 2 error is failing to reject the null hypothesis when the null hypothesis is not true. So in this case, when non-normal data is fed to the test, its power is the ability to detect that non-normality and reject the data. So how we actually evaluate the power, we use what's called Monte Carlo simulation to create population data from non-normal distributions. And then we pull random samples from these populations and we run them through each test. And so like in a study that we're going to be talking about a lot, there was 4,000 samples generated on multiple different distributions using the inverse cumulative distribution functions from random data. And then it was pulled at different sample sizes, 10, 20, 25, 30, 50, 100, 200, 500, 1,000, 2,000 to give kind of an overarching view of what happens at different sample sizes. And at each sample size, you do thousands of tests, whether that's 10,000 different samples of that sample size. And then we figure out, okay, so we know we fed non-normal data. How many of those times at that sample size did the test correctly reject the null hypothesis? And then we divide it by the total number of trials. And that gives us a percentage, and that percentage is the power, okay? But why does power matter? Well, it's the measure of the test's ability to correctly reject the null hypothesis. As I mentioned before, power can also be related to type 2 error, and it's related through one's complement. So power is 1 minus the probability of committing a type 2 error. Type 2 error, again, being accepting the null hypothesis, well, failing to reject the null hypothesis when it would be correctly rejected. I shouldn't say accepting the null hypothesis. And type 2 errors occur when a failing condition is accepted as passing. So it's often called the customer's risk because it's the risk that a failing condition is not identified and released to the customer. So the reasons for limiting risk of type 2 error are twofold. Customers want lower risk, and we want controls that effectively identify failures. So this customer's piece kind of has two meanings. It can mean your organization's actual customer. They want to make sure that your capability analysis is valid because you and your customer are determining whether to move forward on this process based on this capability. You need to make sure that that capability is valid. But customer can also refer to you as the engineer. And the supplier would be the statistical package that is providing the service, or at least the test that is providing the result. And you are the customer because you are receiving the result from that test. And the test would be, so you are also the customer too. And as a customer, you want lower risk. You don't want to be accepting data that is failing. So that's why power matters. And different organizations are going to handle the power conclusions a little bit differently, and we'll kind of talk about some ways to do that. But it is really important because it's a measure of how much we can trust our data. So we can use the power to develop testing strategies that minimize that type 2 error. One good way would be to start with the most powerful tests and only use less powerful tests when previous tests identify a failure. This allows us to guarantee the lowest possible risk of a type 2 error. So by starting with a test that has a very high power, if it fails, then we can use a little bit less powerful and keep moving down. That way we always know that we have minimized our type 2 error as much as possible. So how do the tests compare? Well, the power of tests varies with significance level, sample size, and the distribution from which the data originates. As sample size increases, so does the power of the test to correctly reject the null hypothesis. Again, earlier we were talking about sample sizes. Sample sizes have a huge impact on the power of each individual test, and we're going to see that. It's actually really, really cool. But as engineers, we know more samples means more money. So by using this power comparison, we can really strike that balance between reliable and valid statistical analysis and reasonable costs and reasonable effort in collecting those samples. So based on academic literature, this is a general order. There's only one paper that actually compares all 6 of these directly, but a lot of them compare a couple here or there. And so this general order follows a lot of different research. And you'll notice here that the Shapiro-Wilk has Royston in parentheses, and that is actually because the Shapiro-Wilk, if you remember from our video, can only analyze up to 50 samples. So we use the Royston approximation to go all the way up to 5,000 samples. So the Shapiro-Wilk Royston is what was compared against these other ones in a lot of these studies because they go up beyond that 50 sample point. The Lilliefors, again, is that corrected KS. Ryan Joyner is an approximation of Shapiro-Wilk. And so you'll notice that the Shapiro-Wilk-Royston and that approximation, the Ryan-Joyner, are very, very powerful, both powerful. And here you kind of get to see that cool relationship between the Lilliefors test and the KS test, where the the KS test is the least powerful by far in almost all of the literature. But just by using that test statistic and calculating the p-value a little bit differently, we see the power increase significantly, going from a test you probably don't ever want to use, which is the KS test, all the way up to being what is a great alternative and competes with the Shapiro-Wilk and is even better at certain sample sizes. And we'll see that in a second. But to me, that's just incredibly fascinating, that by taking a test statistic that's calculated the exact same and just a different p-value calculation, you can derive such an immense increase in power. So there's some important considerations when we're doing these power rankings, and that's that the relative power rankings are dependent upon sample size and underlying distribution. So some sample size considerations, we can use these charts from previous research to help determine our order of tests. So here you'll see that as our sample size increases, in most cases, so does the power. So the maximum power is 100% rejection of the null hypothesis, and 0 would be 0%. So this gives us a really great visual representation of the power comparisons. And something that I find really, really fascinating is you'll see that this KS test kind of peaks right here and then sort of flattens out around 16%. Another really cool thing is that in the beginning here, you'll see that the Shapiro-Wilk-Royston is more powerful than the Lilliefors, even though they're very close, and they're basically right on top of each other. But then right between that 50 and 100, the Lilliefors converges onto 100% really, really quickly, whereas the Shapiro-Wilk sort of approaches much more gradually. And then the Ryan-Joyner catches up to that near 100%, right around 500. And something really interesting is that the Anderson-Darling kind of do a swap, with the Anderson-Darling being more powerful at a lower, and the Jark-Bear being more powerful at higher sample sizes, and both sort of leveling off right around a 92% power. So how you could use this graph would be to take your sample size and sort of draw up and figure out the first one test you want to use, all the way down to your bottom. Now there are tables that can help show these a little bit better because this graph is kind of messy, but this is a really great visual representation of how, as your sample size increases, in general, not always, with the KS, you're going to see that. So the KS actually does approach 100% in some distributions, and we'll see that in a second here, because underlying distributions have a very, very important impact. But how do we know the underlying distribution of our data? Isn't that what goodness of fit testing is for, such as normality testing? And that is absolutely the case. In real empirical data, there really isn't an underlying distribution, but we can use the visual shape of the distribution. We can use symmetry and tailoredness to sort of identify and distinguish between two different categories. So skewness and kurtosis are measurements of that shape, and they can actually help us to determine which test to use. So in most power studies, you'll see that they divide them into two different segments: the symmetric distributions and the asymmetric distributions. And you'll really see that most of these tests are less powerful when analyzing symmetrical data, which makes sense. I mean, the normal distribution is a symmetrical distribution. So a symmetric distribution is going to look a lot more like a normal distribution than will an asymmetric. And to me, these graphs just exemplify that so well. In here, the Kolmogorov-Smirnov is basically useless on symmetric distributions. On asymmetric distributions, it actually performs okay at about 25%, maxing around 30%. But on certain distributions, it will approach 100%. But when you have all these other tests, there's really no reason to consider the KS test, except maybe at very small sample sizes. But you can't really rely on your data with small sample sizes anyway. But if you look on the symmetric, almost everything approaches, the asymmetric, almost everything approaches 100% power very, very rapidly. Whereas with the symmetric, it takes quite a while. And the Anderson-Darling and the Jark-Barra actually never approach 100%. And that's really what was dragging them down on that previous one, which was averaged across the symmetric and asymmetric. So this to me is just an incredibly great, just a great example of how the symmetry of your data can really have an impact on how reliable your normality testing is. So you could use like a skewness benchmark to determine maybe it's too symmetric to even rely on testing. Now that doesn't really help you. But it's something that's very good to know. If you have very symmetric data, you just can't trust your tests nearly as much without larger sample sizes. But that doesn't mean that your data isn't normal, because for it to be normal, it has to be symmetric, which is exactly why it has much more trouble. These tests have more trouble with it. So, as I was mentioning, that the distribution has a huge impact, especially when it comes to the symmetry. But when we look at the t-distribution, which is a generalization of the standard normal distribution, we can see that the degrees of freedom actually have an impact. So just because we have a symmetric distribution doesn't mean that our tests are always going to accept. You'll see here that even though they're all t-distributions, different t-distributions have very different behaviors. I believe this top one here is the Shapiro-Wilk-Royston, or the Lilliaphores, and that purple is the other one. But just a fascinating group of graphs here, where we see as that degrees of freedom increases, which you'll see as it approaches infinity, that really does look like a normal distribution. Our tests almost always accept it, and that's probably because in the case of a distribution like that, again, just because it didn't come from a normal distribution doesn't mean the data is not normal enough. That's really what these tests are trying to tell us, is our data normal enough to have valid capability results? Okay, so how often do these tests correctly identify normal data? So this is data that was taken at the n equals 30 samples across multiple distributions. To give you a general idea, let's say you're running a capability study with 30 samples, and you don't know what distribution your data follows most likely. That's what you're trying to find out. Is this normal enough to trust my capability results? Well, you're going to see that the Anderson-Darling is about 29% powerful. The Jark-Barra is about 24. The KS around 16.5. The Lilliaphores is around 67 to 68, and the Shapiro-Wilk is around 72, with the Ryan-Joyner coming around 30. So earlier we looked at the actual rankings, but now we get to see the numbers, and we see that the Lilliaphores and the Shapiro-Wilk, number 1 and 2, are way more powerful than the Ryan-Joyner. So something interesting, maybe a better way to think about these numbers. So let's take the Anderson-Darling. That's a very common one. Lots of organizations use the Anderson-Darling as their first line of defense. At the standard n equals 30 samples, if you have non-normal data, the Anderson-Darling test only identifies non-normal data 30% of the time. That means 70% of the time it incorrectly accepts failing data as passing. So at 30 samples, the Anderson-Darling is wrong 70% of the time. That is wild to me. One of the tests that we rely so heavily at a 30 sample. Now, I'm not railing on Anderson and Darling. Like I said, the whole goal of a normality test is to find out if the data is normal enough. Enough to trust our capability, not to determine did this come from a normal distribution. As engineers, we just care, is it normal enough? But to me, that's wild. A test we rely on so heavily at 30 samples, so heavily, is going to be wrong 70% of the time with failing data. We didn't look at the type 1 error here. That's what our alpha level controls for. But here we see that when given non-normal data, it fails 70% of the time. So let's take a look at the Anderson-Darling, KS, and Ryan-Joyner. So these are the only 3 normality tests that are available in Minitab, which is a very common software in the engineering industry. And these are the only tests it offers. The best you can do at the common sample size of 30 is a minimum of 70%. A minimum of 70% failure using these at 30 samples. Now, again, we're testing to find out if our data is normal enough. So is 30% with the Ryan-Joyner, is that okay? Are we okay with a 70% probability of a type 2 error? If we have no other options, I think sure. But looking at this with the Lilliefors and the Shapiro-Wilk Royston approximation, we don't have to do a whole lot of work. All we have to do is just switch up our test, and we can jump from a 30% power all the way up to a 72% power. To me, that's a no-brainer. 30% would be okay if none of them were that much higher. But when all we have to do is just use a slightly different function in QESuite, the Shapiro-Wilk Royston just makes the Ryan-Joyner look silly at 30 samples, you know? And the KS makes the Lilliefors makes the KS look just unreasonable. So I just thought this was something really important to point out, that yes, 30% might be okay for some organizations, but with very little effort, we can bring that right up to 72 without collecting any more samples. So let's take a look at how many samples we need to get a simulated power level of 95%. So again, this is averaged across all of the distributions studied, and the required sample to get 95% power varies. So we look at the Anderson-Darling and Jark-Barra. They're both greater than 2,000, and that's because at the maximum sample size, 2,000, these distributions seem to asymptotically approach 92. If you remember, that was because if we looked at just the symmetric data from earlier, that approached about 80, and the asymmetric approached about 100, so it never really got above that 92% because of that. The KS test also never approached 100, but instead of approaching 92, it only approached 16.6% and actually reached a maximum of 18.4% around 100 samples. So as the sample size increased, we actually saw the KS test go down a little bit, which was pretty interesting. Lilliefors, even though it was ranked at number 2, it actually converges onto 100% very quickly, with that 95% simulated power being between the 50 and 100 mark. In this study, sample sizes weren't taken between 50 and 100, so that's why there's that range there. Further studies will be needed in order to pare that down and get a more granular view of where that actually occurs. The Ryan-Joyner gets to 95% right around 400. It's like 400. At 400, it's at like 94%, so it's really close to 400. Close enough for an engineer. And then the Shapiro-Wilk Royston, similar to the Lilliefors, converges on that 95% between two different sample sizes checked. That's at between the 100 and 200. So again, these two just really outshine everything else in this entire study. Definitely the most sensitive tests and highly recommended as your first line of defense. Okay, let's talk again about minimizing customer risk, because that is really a great framework. Remember, don't just think about your customer as the customer. Think about yourself as the customer. Think about yourself as the customer of Anderson and Darling, the customer of Jark and Barra, the customer of Lilliefors. You know, they are selling you a product. The product being confirmation that your data is normal. And you need to know whether or not you can trust them. So because the power is the measure of how likely that the test is to correctly identify non-normal, it's a representation of that risk that you are taking on. 1 minus the power is the risk that you are accepting. So using these charts, we can minimize the risk of committing a type 2 error by selecting the most powerful test for our scenario. But how do we decide which test to use? So as engineers, we don't want to rely on one test. I want to throw that out here right now because it's really a good idea to define a testing sequence that steps through different tests if previous tests fail. You don't just have to use one if one passes. Let's say maybe you always do a double Shapiro-Wilk Lilliafor. That to me is probably your greatest option. Shapiro-Wilk and Lilliafor. If both of them fail, then you move on to Ryan Joyner. If one of them fails, I would say you can probably take it based on this evidence. You've really got a very low chance, but again, you really want to start with the most powerful. But it doesn't mean you have to stop once you get a failing result. Once you get a passing result. Another thing is that the power of all these tests is impacted by sample size and the symmetry of the distribution. So you really do want to take a look at your sample size. Maybe you want to use the Lilliafors before the Shapiro-Wilk and the Jark-Barra before the Anderson-Darling if you're doing a 70 sample size, as opposed to doing a 30 sample size where you'd use the SW and the AD first. It's really up to your organization, but I highly recommend using research like these studies that we're talking about to figure out what that order is. That way, when you're talking to a customer, they can say, well, why are you okay with failing on the Shapiro-Wilk but passing on the Anderson-Darling? Well, because the Shapiro-Wilk is a very powerful test. The Anderson-Darling isn't that much more powerful, but the power of the Anderson-Darling is acceptable in our scenario. And maybe your customers say, well, it's not for us. We're not okay with a 70% failure rate when you have non-normal data. We need a minimum of 60%. So maybe you have to increase your sample size. Maybe if your data is too symmetric, you say, well, this is pretty symmetric, so we're not sure. But the good thing is that the normal distribution is a symmetric distribution. So in order for it to be normal, it has to have a good degree of symmetry. And they'll go, oh, okay, yeah, that makes sense. Even though the power is lower because you're testing more normal data, right? So the power isn't an exact measurement. So we have to use our knowledge of statistics and normality tests and our engineering method to pick the right tests. And that's really what this video is designed for, to give you those tools. Okay. So conclusion time. Normality is important in engineering. I don't have to restate that. I think we all understand that one. As engineers, we do need a method of discriminating between data that is normal enough and data that is not. Normal enough is in quotations here because that's really all we care about. Going back to that whole symmetry versus asymmetry. Normal, for it to follow the normal distribution, it has to be symmetrical. So we can accept a lot more type 2 error with symmetrical data because we know that it's more normal in that case. We just want to know what's normal enough, and as an organization, that's your job to determine what that normal enough point is. That's what your p-value, your critical p-value of 0.05 or 0.025 or 0.1, whatever your organization determines, that's how you guys are selecting for normal enough data. Okay, so again, it's best to use multiple tests. Just because you pass the Shapiro-Wilk doesn't mean you shouldn't use the Lilliafors. Later we might talk about what each test is sensitive to, but right now this is really about type 2 error, risk, and how much is acceptable. So we can use this academic research to define procedures that use tests in order to minimize risk of type 2 error. That's the key here. Engineering organizations love statistical process control. That's the new big thing right now. But just using the statistics isn't enough. We have to understand the math behind them. That's why we make all these videos, so that you understand the math, so that when you're talking to a customer, you can tell them, yeah, we passed on the Anderson-Darling, but I don't trust it. Our data's not symmetrical enough or whatever. That's the underlying knowledge is what's really going to help you, and we can cite academic research to help create these standards. That way these aren't just standards that are set because, well, the Anderson-Darling is in Minitab and it's really easy to run. Not just because, well, we execute in the order of Anderson-Darling, JARC-BERA, KS. We only do 3 tests because 3 tests is enough, and we do them in alphabetical order. Now, in that case, we got lucky. AD is more powerful than JB is more than KS at lower sample sizes. But let's say you have access to the JARC-BERA, the Kolmogorov-Smirnov, and the Ryan-Joyner. You're going to run the JB, then the KS, then the RJ. Well, that doesn't make sense because your RJ is much more powerful than the other 2. So that should really be your first test. So again, this academic research can help us create standards that are based on real experiments, real simulations, and just gives us a much more reliable method of creating these standards. So two things that I want to end on here with is that organizations have to decide the minimum acceptable risk of type 2 error. Again, going back to those charts, we can figure out what the simulated type 2 error is of these distributions. And we might have to adjust our sample sizes to accommodate. So let's say that your organization says, well, we really, really do want to have a 5% type 2 error. We have a 5% type 1 error because we defined our p-value as 0.05, right? We really want a 0.05 type 2 error. That means a power of 95. So we're going to have to increase our sample size no matter what, because the test that converges on that 95% power is the lucius that does it first. And that's not even until 50 to 100 samples. We just can't rely on 30 samples. Or maybe say, you know what? We just can't justify moving up to doing 100 samples. It's just way too many samples for us. It costs too much money. We're good with the 30. We can accept this type 2 error. But you know what? KS test, we can't. We just can't use. AD, JB, I'm sorry. You guys just aren't powerful enough at that 30%. Although if you're throwing out the Anderson-Darling, you better throw out the Ryan-Joyner at 30 samples because Ryan-Joyner is right at 30.23 or whatever, and Anderson-Darling's at 29. So is there really that big of a difference at 30 samples? So again, that is really what this video is to do, is to give you the tools to make those decisions. If you have any questions, please reach out. We'd love to share some of this research with you. It's incredibly fascinating. We've got some of the raw data. We would love to show you. That way you can create real standards that are based on something other than what is available. And then the last thing I want to finish on is our recommended testing order. This is across all sample sizes and distributions, and this holds true pretty much for asymmetric or symmetric at all sample sizes. You're just going to see a couple of switches between Shapiro-Wilk and Lilliefors and the AD JARC-BERA. So just know these two are pretty much comparable, and these two are pretty much comparable in any scenario that you're really going to be looking in. So the recommended test order is Shapiro-Wilk, Lilliefors. Again, those are interchangeable. Ryan-Joyner third. At really low sample sizes, it can be interchangeable with the Anderson-Darling. At the 30 especially. Above 30, AD and JB are going to be interchangeable. And then in no scenario is the KS ever going to be anything other than 6. So that's our recommended testing order. Again, if you would like the raw data, the research on this, please reach out. We would love to go over that with you. My email down in the link in the description, or you can always email our helpline at rr.help@engsuite.org. This is a topic that we're very passionate about, because the whole goal of QESuite is to provide manufacturing organizations with not only the tools, but the information to create excellent quality standards and quality systems that really, really capitalize on the technology and the knowledge of today, something that we haven't always had, especially in the manufacturing world. So we would absolutely love to talk to you. All right, I know this got long, but thank you so much for watching. This is an incredibly important topic. Have a great day, and please do something awesome.